Hi and welcome to a lesson of partial differential equations. So in this class we are going to talk about the homogeneous wave equation. That is a second order partial differential equation with constant coefficients. Now, as we talked earlier about heat equation, where we have an equation having the partial derivatives with respect to t and with respect to x. And similarly, in this problem, also we have the partial derivatives of the function with respect to t and with respect to x. But here we have the second order partial with respect to t, and in the case of the heat equation, we have only the first order partial derivative with respect to t. Now the idea is the same as we did earlier. Now the LT inverse operator in this case applied on the function will be the iterated integral over the domain of time applied to the function, and the LX inverse will be the iterated integral over the domain of x applied to the function. And because LT inverse operator is the iterated integral, because the LT operator is the second order partial derivative in the case of the homogeneous wave equation. Now let's start solving the problem in the t direction. So let's apply the LT inverse operator on both sides of the equation, and then simply expanding this inverse operator, since we are integrating over the domain of t, and this is the second order partial derivative with respect to t. And on the right hand side we will keep this as it is. Now if we integrate this function, what we are going to get is the first integral is going to give ut of x comma t from 0 to t dt, which is equals to 0 to t ut of x comma t minus ut of x comma 0. Now if we again integrate this function, we are going to get u of x comma t minus t ut of x comma 0 over the domain 0 to t. Therefore, we will get u of x comma t minus u of x comma 0 minus t ut of x comma 0. Now this will be the left hand side of this equation. Therefore, the left hand side is u of x comma t, and if we shift all this stuff, that is the initial conditions of the problem, to the right hand side, we will get ux comma 0 plus t ut x comma 0 plus lt inverse lx u. Since this uxx, we can write it as lx u, right? Now the initial conditions are given in the problem. U of x comma 0 is sine x, ut of x comma 0 is 0. Therefore, we will just insert the conditions. Therefore, ux comma 0 is sine of x plus ut x comma 0 is 0. Therefore, this component will be 0, and this will be LT inverse LX u. Now, what we need to do is we need to identify u naught. Therefore, u naught is the component that comes from the initial conditions. Therefore, this is sine of x. So we have u naught equals to sine of x. Now if we need to find u1, therefore the inverse operator is applied outside, which means we have to integrate over the domain of t, and LXU implies we need to differentiate this function with respect to x twice, right? Like this, dt. Therefore, u1 equals to the second partial of sine x is negative sine x. So we get the iterated integral over the domain of t negative sine x dt. And if we integrate this, we are going to get the first integral will give us t sine x from 0 to t, which will again be t sine x. And again, integrating the function gives negative t squared over 2 factorial sine of x. Now, similarly, if we want to work out for u3, that is again the iterated integral, and operated on this u2, that is lx u2. Therefore, the second partial of this negative t squared over 2 factorial sine x will be t squared over 2 factorial sine of x dt. Therefore, u3 will be, sorry, this is u1. This will be u2, not u3. So u2 is equals to t to the power 4 over 4 factorial sine of x. And in the similar manner, we can find out u sub 3 and u sub 4 and so on. Therefore, the function uxt is nothing but the series expansion of all these u functions. Therefore, if we collect all the terms, we have sine x, and then u1 is negative t squared over 2 factorial sine x, and then positive t to the power 4 over 4 factorial sine of x, and so on. Therefore, if we take sine x as common, we have 1 minus t squared over 2 factorial plus t to the power 4 over 4 factorial, and so on. And this function is nothing but the Taylor series expansion of cosine t. So this is the result of the problem, answer to this problem satisfying the boundary conditions, right? Now, in the similar manner, we can approach the problem in the x direction. So now let's apply Lx inverse on both sides. So Lx inverse means we need to integrate the function or the domain of x. Therefore, this we can write it as Lx inverse LTU, and Lx inverse applied on this function gives ux comma 0 minus ux comma t ux comma t minus x ux 0 comma t and minus u of 0 comma t. Now, if we collect the terms onto the right hand side and just isolating ux comma t on the left side, we get x ux of 0 comma t plus u of 0 comma t plus Lx inverse applied on LTU. Now, since this component is given in the boundary condition, that is u of 0 comma t is 0, therefore this term is 0, and for ux 0 comma t, we know that this is a function of t. This is a function of t, therefore now we can write it as u of x comma t equals to x h of t plus Lx inverse LTU. Now, since u naught here will be the term that is from the initial or the boundary condition, therefore we have u naught equals to x h of t. Similarly, u1 equals Lx inverse means the iterated integral over the domain of x applied on LTU. So this gives h double prime of t, because the LT operator is the second order partial operator with respect to t. If we differentiate this twice, we get this thing, right? Now u1 will be equals to x cube over 3 factorial h double prime of t. And similarly for u2, again we need to integrate in the similar manner. Therefore we will get x cube over 3 factorial times the twice partial derivative of this h double prime, which gives the fourth derivative of this function h of t, which again on solving will give us x raised to the power 5 over 5 factorial h fourth derivative of the function h of t. And similarly we can find u3, u4, and so on. Therefore now the solution is governed by the series, sum of the series of all the u's. Therefore u0 is x h of t plus u1 is x cube over 3 factorial h double prime of t, and then we have plus x raised to the power 5 over 5 factorial h, the fourth derivative of h. All right, and so on. Now this h of t is unknown in the problem, therefore we need to find this h of t, and we will use the initial conditions in this regard. Therefore let's use initial conditions to find what h of t actually is. Now the initial condition, that is u x of 0 equals sine x. This gives sine x equals x h of 0 plus x cube over 3 factorial h double prime of 0 plus x to the power 5 over 5 factorial times the fourth derivative of time at t equals 0, and so on. And now the sine x has the Taylor series expansion as x minus x cube over 3 factorial plus x to the power 5 over 5 factorial, and so on, equals to the stuff on the right hand side. Now if we compare the coefficients, h of 0 equals 1, h double prime of 0 equals 1, and similarly the fourth derivative at 0 will again be 1. So all the derivatives are 1, therefore the h of t can be expanded in the Taylor series form. Therefore we have the Taylor series expansion of function as h of 0 plus h prime of 0 times sorry, okay, so times t plus h double prime of 0 times t squared over 2 factorial, and so on. Now we have something missing here, that is the first derivative, the third derivative, and all these odd derivatives are missing. Therefore we can now use this boundary condition, that is the this initial condition, that is utx comma 0 is 0. Therefore if we find ut of this function here, this function here ut, so ut will give us x h prime of t plus x cube over 3 factorial h triple prime of t plus the x to the power 5 over 5 factorial and the fifth derivative and so on. Now this is equals to 0, which means that h prime, sorry, this is 0, 0, which means if we compare the coefficients, so h prime is 0, h double prime is 0, and so on, all the derivatives we are going to get are equals to 0, right? Therefore, now this and this function, okay, we only have the derivatives of the function for u as h double prime and h fourth prime, so we don't need these derivatives as well. But if we need these, we can just find like this way. Now if we plug in the values of the derivatives, so we get u equals x. Okay, so h of t is this function that is equals to 1 plus t plus t squared. Okay, t, not this t, because h prime of 0 is 0, so 1 plus 1 plus t squared over 2 factorial plus t to the power 4 over 4 factorial and so on. And here I think that something is missing. That is, this h double prime is not positive one, it's negative one. I'm sorry, this negative one, so this stuff will be negative. Okay, h prime, h of 0 is 1, because here we can see if we compare this with this x, h of 0 is 1. If we compare this one, so h double prime of 0 is negative 1, not positive 1. I mistakenly write as positive 1. Similarly, the fourth derivative is going to be positive 1, and the fifth is going to be negative. So this term here is negative. This term is here negative, and then again the terms will be negative and then positive and so on. Now we can see here that this is nothing but the Taylor series expansion of the function cosine of t. Therefore, the solution to this problem is going to be u equals x times h of t. Therefore, this is cosine of t. Okay, then plus x cube over 3 factorial h double prime of t. So h double prime of t is negative cosine t plus x to the power 5 over 5 factorial, the fourth derivative, that is going to be positive cosine t and so on. Therefore, if we take cosine t as common, we are going to left with x minus x cube over 3 factorial plus x power 5 over 5 factorial and so on. And this is nothing but the Taylor series expansion of sine x. Therefore, the solution to this problem is going to be u equals cosine t times sine of x. Now we can simply verify the given boundary conditions and the problem. So u of x comma 0 is going to be sine x. Therefore, if we put 0 here in place of t, we are going to get sine x. Then ut will be negative cosine t sine x. Therefore, ut of x comma 0. Okay, it not be 0. It's something missing here. No, it's ut x comma 0 is equals to 0. Therefore, this will be sine of t, not cosine to negative sine of t. So negative sine of t times sine x. So if we plug in t equals 0, we'll get 0. And again, we can verify the boundary conditions and the equation as well. So this is the way you can approach this problem. It's pretty simple if you are moving in t direction, but if you are moving in x direction, then you have to do some extra stuff. So because we need to find the function of t, that is h of t, and for that we are going to use the initial conditions, right? So that's all for the today's lecture, and in the next class we will talk about the problems having time dependent boundary conditions. So thanks for watching the lesson. That's all for the time being.